Good morning, friends. I hope you are able to follow the lectures. I understand the limitations, and this is our Mann Ki Baat session. As I am being telling, I also spent some time with these lectures, these videos, and then I try to think that I am doing my BTech course, that is 77, 82 in IIT Kanpur, and what sort of feeling I used to have when professor used to come and write lot many equations, lot many theories. At some point of time, I used to tell myself, bahut ho gaya, enough is enough. Then what is the best way we were handled? Was we are given assignments, and also in the lecture, whatever theory has been explained, some numerical examples were given. Why this is important? Please understand, if you want to be really successful and you are sure that you have understood, there is a better way of checking it. Whatever I understand is, I believe there are three steps are there. One is know-how, so I have learned from theory. One is do-how, I should know how to implement it. And finally, it is the show-how. Okay, when you use this know-how and do-how to produce a product. Okay, in this case, an aircraft. So now we'll, believing in this understanding, know-how, do-how, and show-how, we'll be attacking the do-how part. That is, we will try to understand how this theory to be implemented for practical purpose. And I have taken the example of standard atmosphere. I'll be solving one practical problem. Okay? Let us say that I want to calculate standard atmosphere at h equal to 14 kilometers. This is my question. And what do I mean by standard atmosphere? I am asking for, do I know pressure, density and temperature? At the same time, I know that temperature data versus altitude has been generated experimentally by firing sounding rocket, launching weather balloons for different places, and then some average value have been taken. These average values were used to represent the variation of temperature with altitude, which is here, which we have already seen. Please understand, this is experimentally generated. This is the starting point. Okay? Now what is our question? Our question is, at h equal to 14 kilometer, what are our pressure and density? Temperature anyway, we know from this variation, which is agreed by every team, every organization working in aerospace, right? So let us see, when I see this is to be evaluated at h equal to 14 kilometer, I should immediately see the temperature variation. Okay, that is the starting point. And in that we know at sea level, in standard atmosphere condition, these are the values. Pressure is 1.01325 kg per meter square, density is 1.225 kg per meter cube, and temperature is 288.16 degree K. And of course, this PS standard, the pressure we are meaning static pressure. Okay? Whenever we say pressure and we don't mention anything associated with it, we are actually meaning static pressure. So if I want to find at 14 kilometer, which will be somewhere here, let's say this is the point which is h equal to 14 kilometer. It's very simple. From here, I have to start and find what is the property here. I know from here to here, there is something called gradient slope, and then there is an isotherm. So there are two regions, and we know by now how to calculate the properties using P equal to rho RT, that is, I'm assuming air to be perfect gas. Since it is h equal to 14 kilometer, I immediately see here, okay, I see here and I find 14 kilometer means the temperature is 216 0.66 degree Kelvin, which I have written here. This I am directly getting from this chart. Okay. In practice, you will find there is a standard atmosphere table generated, right? You can do a Google search, you will find, and I am trying to give you an example how that table was generated. Okay. A specific case, I have taken H equal to 14 kilometer. What are the value of pressure, densities, and your temperature we know. So first, what I do, I mark it point B, and let me call it point A. I will first see up to 11 kilometers, that's point A to B, because there is a gradient part because the temperature has a lapse rate, okay? And then from 11 to 14, it is isotherm, that is temperature is constant. We have already developed relationship for the gradient region as well as for isotherm. We have to simply apply that. Let us do that. If you see in the gradient region, the lapse rate, which is dt by dh, is how much? This point is 216.66, so this will be 216.66 minus 288.16 by 11.0 minus 0. Okay? This is the standard condition, 288.16. This minus this, and height is 0 and 11 kilometer. So this I get as minus 0.0065 Kelvin per meter, which is, you know that, lapse rate is this. It's nothing we are calculating because it is the way we have plotted this altitude and temperature variation through experimental data. Now, in the gradient region, what are the relation? If we check the notes, it is P by P1 is equal to T by T1 into minus G0 by AR. R is the gas constant, and rho by rho1 is T by T1 minus G0 by AR plus 1. What was G0? G0 is the sea level value of G, right? G0 concept is used for geopotential height. So that is 9.8 meter per second square. Now, what should I plug? I want to find pressure at 14 kilometer. Pressure at 14 kilometer we want to find out, but we are now first finding pressure up to B, 11 kilometer, because up to B, it follows the gradient law. That is, up to B, these relationships are available and valid. Okay. So first I find P11 by P1. What is P1? P1 is the standard atmosphere here, which I know. T and T1. T1 is the standard atmosphere, and T is T at 11 kilometer, which also I know as 216.66. So if I substitute this, what I get? P 11 kilometer is 1.01325 into 10 to the power 5. That is the P at sea level into T is 216.66 divided by 288.16 to the power minus G0 is 9.8. And what is A? A is minus 0.0065 into R is 287 in SI unit. Right? So this will give me P at 11 kilometer equal to 2.26 into 10 to the power 4 Newton per meter square. Is it clear? I have just substituted the values. Okay. Similarly, if I substitute for rho, I get rho 11 kilometer is equal to 0.367 kg per meter cube. Try to develop a feel for this number. If we are flying at 11 kilometer, the pressure is 2.26 into 10 to the power 4. And what is the atmosphere? Atmospheric pressure at sea level? it is 1.01325 into 10 to the power 5, okay, into 10 to the power 5 kg per, this is Newton per meter square. Sorry, this is to correct it, okay. This is 1.01325 into 10 to the power 5 Newton per meter square, okay. It was 1.01 in 10 to the power 5 and here it is 10 to the power 4 into 2. So pressure has reduced so much. So what will happen? Suppose if the cabin is pressurized with, let's say, with atmospheric pressure or a little less than atmospheric pressure, generally calibrated with 6,000 feet, 5,000 feet, 8,000 feet. Let's say, for assume it is just atmospheric pressure. Then the difference is so much that if there is a crack on the windshield, things inside will be thrown out, okay? And also, if we do not take proper care, okay, with the understanding that there is so much of difference in pressure, our structural design also will not be appropriate. So we have to be very careful when we are designing an airplane. We must see at that altitude what is the pressure difference, okay? So that way this is, and most of the airplane, jet engines and all, you'll find they will be flying at 11 kilometer, which is tropopause. Okay, so 11 kilometer values we now know. Okay, we have to go to 14 kilometer. So what is the way? Now you know that you have to apply relationship which were used for tropopause. So let us go back and check what was the relationship for tropopause. So our problem is now, this is the point B. Now I know P is 2.26 into 10 to the power 4 Newton per meter square, and rho is 0.367 kg per meter cube. I have to find at 14 kilometer, and this is 11 kilometer. So we'll check what was the relationship for tropopause. If you check your notes, you will find P was given as P1 e to the power G0 by RT into H minus H1. Similarly, rho was given as rho 1 e to the power, same expression, G0 by RT into H minus H1. What is P1 here now? I am going from 11 to 14. So basically I want to find at 14 given P1 which is at P11 kilometer. Again I want to find rho at 14 given rho at 11 kilometer. These two values we have already calculated. I will have to just substitute that, and for H minus H1 what should I put? H minus H1 means from here to here, H is 14 kilometer. What is H1? H1 is 11 kilometer. So this difference is 3 kilometer, and to be consistent, this unit is 3000 meter. Okay. Now simply substitute here. What about temperature? You know it is tropopause. It is tropopause, so whatever temperature was here, same will remain here. So this is 216.66 degree Kelvin, and if I substitute this, then I get value. I get P at 14 kilometer as, you please do it yourself. This is very explicit now. Newton per meter square, and rho at 14 kilometer is 0.023 kg per meter cube. Please the calculation yourself. I may commit some error. Although this example I have taken from a book by Introduction to Flight by Anderson. There are plenty of books you can use, you can refer. But mostly you'll find examples I am picking from Anderson. Then there's a book of Stability and Control by Nelson. Do a Google search, you'll find so many books, right? So what is the message? That once this temperature profile is given, which is measured and agreed based on experimental result, you ask me any altitude, I can find out the pressure, density and temperature. Temperature anyway is known, right? That is how whole atmospheric table is created. And the table will be given H, what is the pressure, what is the density, what is the temperature. So you can look through the table and find out. Okay, so this is the basis of generation of standard atmosphere table. This is clear? Okay. Now second part, which also I want to solve a problem so that you are clear about in your mind what you are doing. We talked about pressure, density and temperature, altitudes. Right? Let us quickly recap. What is the pressure altitude? What we are telling? That suppose an airplane is flying at 11 kilometers and it is sensing some static pressure. Okay? Now, the pressure altitude is defined like that. Whatever static pressure it is sensing in reality, you now come back and see the standard atmosphere table and see what is that altitude in standard atmosphere which will record this much of static pressure, right? That is, if I am flying at an altitude, there is some static pressure, I have some value, then I check the standard atmosphere and look for static pressure, this static pressure, and what is the corresponding altitude in standard atmosphere. So I call that pressure altitude. Similarly, temperature altitude, and then I know density altitude because P equal to rho RT, I find density altitude. From there I again find out what is that density, then I check in the standard atmosphere, what is that altitude that gives that much of density in standard atmosphere. As simple as that. It will be clearer once I solve a problem. Let's say, suppose an aircraft is flying where actual pressure and temperature are 4.72 into 10 to the power 4 Newton per meter square and temperature 255 degree Kelvin respectively. Okay? Question is, what is the pressure altitude, what is the temperature altitude, and what is the density altitude? What I will do now, I will take this number, this much of pressure, then I will go to the standard atmosphere table, I will find out where is this pressure and check what is the altitude that corresponds to that pressure. That is, I will see standard atmosphere table and look for this pressure and corresponding value of H, that will be the pressure altitude. In this case, it will be, you will find that it will be pressure altitude will be 6 kilometers. Right. Then for temperature altitude, again same thing, so mechanical. What is the temperature recorded? 255 degree Kelvin. Then from there, go to standard table and see what is the corresponding altitude in standard atmosphere as far as H is concerned. So that H you will find is around 5 kilometers. Right? Okay? So now, to find the density altitude, what we'll do is simply first find out the density. How do you find density? I write rho equal to P by RT from the perfect gas law. So I'll find rho equal to 4.72 into 10 to the power 5, which was the pressure recorded, 4.72 10 to the power 5. Then divided by R, we know 287, and T we have recorded as 255. So I get a density value 0.643 kg per meter cube. Now it's very simple. I go to standard atmosphere table and see this density corresponds to what value of H, and that H will be, in this case will be 6.24 kilometer. So this becomes my density altitude. Correct? So you could see, although the aircraft is flying at a fixed geometric altitude, but their pressure altitude, temperature altitude, and density altitudes are different. That should be borne in mind. Now it's obvious, you should be able to answer this question. At what altitude the pressure, density, and temperature altitudes are same? The answer is at sea level. Okay? Thank you very much.